I will tell you that never expect to learn a programming language from a class. I mean, I never ever took a programming class, and for various reasons. It's not that I chose that; it was not there or it was not interesting. But somehow I learned to program because uh, it's much more fun if you have a intention to do the program, so to program something or to do some calculation. It's much more fun rather than having a programming class for itself. So for us physicists, I think that that's a better way to learn. I mean, then you have an intent to learn. Otherwise, it will be very boring. So, and it will be very practical also. So that's why I would say that don't wait for someone to come and teach you a course in Python or Mathematica. Then it will never happen actually. I mean, even if it happens, then you will wait for that. I mean, how long will you wait? So better you just start and start by yourself. It's best to self-learn. Okay. Okay. So now I will talk about as I will continue to this infinite dimensional system. And the first thing I will tell, okay, by the way, I forgot to mention, I think I mentioned last time, I brought your graded sheets. So you can come today after the class till around 3 to 3:30 p.m. After that, I leave. So, and come to, I'm in this registrar's office and you cannot take the graded sheet with you. So you can take the graded sheet. I have the solution and question paper. You can check it right there and tell me if you have any objection. And try to do it by today because I don't plan to carry all these sheets from there to here tomorrow. And I have no place to keep it here. So let's get rid of this process by today. Today by 3:30. Okay. So now I will continue to discuss where we finished last time, and we discussed that we started discussing about infinite dimensional and continuous Hilbert space problems. And as I tried to convince you earlier that this is nothing new, it is exactly the same, except the difference is it's infinite dimensional and continuum. Only one non-trivially new thing happens because of that is the existence of generator, the Lie group and Lie algebra, the existence of generator and their commutation relation with the measurables and all that. But apart from that side, we are not discussing right now. What we are discussing right now is, well, it will keep coming into our discussion, but what we are more interested is about the dynamics and statics of the problem. So we stated that this is the form of the Schrodinger equation, which you are, of course, familiar with. IH bar del psi del t. And I stated that this and the static version of this is this. Actually, x. There is no time in this equation. And I stated last time this should not be treated as a tautology, which means it is not like h psi equal to e psi. So this is not, this thing is not e operator. Okay. And I argued that the reason it is not, sometimes some places you will see that it is stated as a e operator. And then it is like saying that F is equal to ma is means that the force is ma. So force is not ma. Force is, you have to calculate force by some other way. This is equal to ml. That allows you to say that the acceleration and times mass becomes equal to the force. But when you say it, you should not think it like force is defined as ma. Okay? Force is, you have to calculate the force by something else, tension, spring constant, something else, right? So this is exactly same as that. It's the statement, and this is, I want to mention this because some books write it like that. So that this is basically energy operator. And Schrodinger was not dumb that he wrote the same thing twice in two sides. So what is this then? So this is basically the rate of change of the wave function. So the rate of change of the wave function is equal to the h psi. So, and we know how it came. It's an infinitesimal version of this thing. This is actually the equation. Its infinitesimal version is this, and this is the static part of that, which is again an eigenvalue equation. Okay, I hope everybody is clear about this point. So now I will start discussing various problems of this form. And the first problem I will discuss is the trivial most problem, that is Vx equal to 0. No potential, no force. Well, ideally, any Vx equal to constant means no force, but let's fix that constant to be 0, and that is the problem of free particle. Now, we have seen free particle in classical mechanics. A free particle, we know the law of free particle. It will, it's the first law, which is basically it will keep. Well, first law is not actually just a law of free particle, but rather it's a definition of an inertial frame, that wherever that is true, that is considered as an inertial frame. But a free particle is it will follow that it will keep moving if it is moving at the same velocity, or it will remain static. So what is that? What will happen in quantum mechanics? How do I describe a free particle? So we must have a, first let's write the position and momentum equation. So the position momentum equation will be, so you will see that in quantum mechanics free particle is a weird thing, even one free particle. This is the, I just wrote this equation and inserted x prime and resolution of identity here. Stuff. So this basically, and similarly I can take the p psi equal to p psi and rewrite it as now you can obviously solve it very easily, because this is nothing but I h bar del x. Because there is a delta function, I don't need the two of them. So this acting on psi x prime will give you p psi x prime. And you know this is a simple first order differential equation. We have seen this before. Its solution is psi x e to the power I p x by x. So that's how we got the solution, psi x prime actually, but let me just, it's a dummy variable, so I can replace it by x. So this is my wave function of a free particle. A free particle means something that has a position and momentum and also energy. So let's now check the other equation, that is x prime h double prime x double prime psi equal to e x prime psi. So this is 1 by 2m minus I h cut del L del x square psi x equal to e psi x. So plug in this thing here, e to the power I p x by h bar, and you will end up with this e to the equal to p square by 2m, which is consistent with the energy of a free particle. Okay? So that tells you that this is a consistent equation that satisfies this, and this. Okay? This solution. In the position basis. Okay. Now this is also something we have. It's not that we are seeing it the first time, because a free particle is already discussed before in the form of de Broglie wave, where we have found the following relation, that E is, so this is, so de Broglie wave was the first attempt to unify wave and particle, the wave particle duality. So what de Broglie made an hypothesis that the wave attribute must be related to the particle attribute, and the relation will be this. Okay, and lambda is h by p, This is a wave attribute, a frequency, a wave number, and a wavelength. And these are particle attribute, which is momentum and energy. And this is, if I write it in this form, this will become e to the power I kx. Now, those who have followed this assignment, that I asked you this question, that so the strange thing here is that it's not like any wave. It's a wave whose wavelength is dependent on momentum. So then I ask this question. So let's say I have a free particle. I have a free particle and I have a moving frame. Now the frame is moving at momentum p, or at velocity v, which is equal to m. Now in that frame, this particle's velocity is 0, momentum is 0. So therefore there is no wave. Okay. So then how do you make sense of interference or quantum probability or anything? Because if I have also, like, let's say I'm doing this double slit experiment, and I am in a moving frame, same velocity as the electron, then I should not see any interference. And that means it seems like quantum mechanics is a frame dependent phenomenon. So that was the question, I think, first assignment. All of you know the answer, right? Avoiding eye contact. What? Some of you don't know the answer to this yet? Or I gave the answer, by the way. So the answer is, this is not a wave in physical space. This is a wave in probability, in Hilbert space. So your momentum will be, it will be always like a, there will be always a finite momentum. Still, one must still ask this question, that what momentum should I use? Because different frame has different momentum, right? So then what momentum should I use in order to calculate the wavelength? So it turns out you should use the proper momentum. Do you know the term proper momentum, proper coordinates? Okay, you will learn it in relativity. So in its inertial frame, you should calculate the momentum. For example, in this experiment, if I think that, okay, this particle is static if it is a moving frame, but then the slit is moving, right? So then in the slit frame, there is a velocity. So that's what you have to estimate in order to estimate the interference velocity. But modulo that, this point is clear to you, that why you don't, this is not a physical wave which is coming like this and like. It's a wave in Hilbert space which helps you to predict what will happen in real space. So you cannot think this in terms of a moving frame picture. Okay, so now this was the free particle wave function. So now so of course this form was already guessed that by de Broglie, but and de Broglie and subsequent people, but now I get it formally by our formalism. So now I want to write the full wave function. So the full wave function is I xt is proportional to e to the power I kx minus omega t, where k and omega are related to e like that. You can still ask, why did I write this form? That is simply because you can plug it into this time dependent form, and if you, this form is consistent, a solution of this time dependent function. Okay. So now let's check that. I will show you in a moment. So k is, okay, I have already written that, but let me write that again. So p is h cut k, e is h cut omega. Okay. Now you can ask still one more question, that it is not the e to the power I, because if so let's look at the solution and see how it is consistent. So p psi xt must be equal to p psi xt. So that can be checked by I h bar del x xt p, and so you plug in, you will see this equation satisfied. H psi xt, E psi xt, and the time dependent. So let me write the time dependent. I want to discuss the time dependent form. that is equal to the E psi xt, and this should also, so plug this in and you will get this equation, and because this is nothing but H is nothing but P square by 2m psi xt equal to E psi xt, and it must satisfy this equation. Actually, let's eliminate all these steps. You can just plug in. I'm just rewriting the same thing. So just this. So this solution satisfies all these equations. So this is a solution of all these position, momentum, and energy form of Schrodinger equation. And finally, it must satisfy. So this is where the catch is. So finally, it must satisfy this. And it doesn't, right? Because we have already discussed this thing is not going to satisfy this when you integrate over the x. It will rather give you a delta function. And that means a free particle solution is not normalizable. So it's an unphysical solution. But still it is useful. So I'll explain you why it still makes sense, why it's still useful, but mathematically it's not a normalizable solution. Okay? So now let me ask one more question. So I have argued that this form satisfy all these things, right? So I have argued that this form satisfy all this. But is this the only form that satisfy this? Because as you probably know that you can also replace this. You could have also done this instead of this. So I wrote down a solution and then I claim this solution satisfy all these equations. But turns out there are other forms also that satisfy. So any periodic function will satisfy this, any sinusoidal function. In fact, I can write also a solution of this form. Like I could have written this also, cos kx minus omega t or sin kx minus omega t. That is something you have learned in wave mechanics, right? That your cos will also satisfy this, sine will satisfy this, and therefore their cos plus I sines, which is e to the power I, will also satisfy this. But then why did I write this? And if that is the case, why do I need complex number? So can somebody argue that why this is not a good solution? No, I'm saying I claim that this function, the solution of all these equations, the Schrodinger equation of a free particle, the energy eigenvalue, the momentum eigenvalue, the position eigenvalue equation. So that's why I should consider a free particle wave function to be like this. But what I'm saying that you can probably already know this form of solution. This will be also satisfying, right? Because if I take derivative of cos twice, I will get this minus sign, because cos will go to sine give the minus sign, and this side you will get the time derivative. So which is a single derivative. So then why I am not considering this as a physical solution, or should I also consider this as physical solution? So that is the question. So did you follow the point? Okay. So it turns out that if you are not so this is a solution of Schrodinger equation, and this is also a legal solution of Schrodinger equation, right? So what is the difference between these two waveforms? Very good. So one is right moving, another is left moving, right? So until measured, it should be both, right? It should be a superposition of right moving and left moving. But let's see what happens when you superpose them. So cos kx minus omega t plus cos kx plus omega t. Okay, let's say some equal superposition. So then you get 2 cos x cos omega t. So do you see the problem with this solution now? So this solution vanishes as kx equal to n pi. Okay. So kx equal to n pi and also omega t equal to n pi. Now this is a more serious problem. N pi by 2 or n pi? Ah, you are correct. But this is a very serious problem. Why? Because it implies the particle will vanish at every time when it hits this. That means you are violating particle conservation. So therefore, you have only one choice, which is if I take left plus right, it must be and this is basically 2 cos kx e to the power minus I. Then there is no such problem. Okay. Okay, good. So now I will talk a little more about this solution as a stationary state solution. So this is another point I actually told you to think about. I do not know if you thought about it. That why do I call it a wave equation, even though it is not of the form? Because you have seen this kind of wave equation. Right? Double derivative in both sides. But this is one single derivative in time. So why it is still a wave equation? Have you studied various kind of differential equation? Or you have never, did you ever encounter a differential equation of this form, which has unequal number of derivative in both sides? You did, right? Why? It looks like I am speaking in Hebrew or something. So this form of equation are called heat equation. So you will see that in heat transport, actually you will get this kind of single derivative, double derivative equation, and it's still a wave equation because it has a solution of the form x plus minus bt, f x plus minus bt. Okay, that's the definition of a wave equation. But there is something more into that. So that I will not, because given your current state, I will not enter into that discussion. There is something really deep and profound about it, that why there is a single derivative. And that comes from the fact that while optics is an attempt to, it is related to the fact why an optics is a, you can see an optical path as a least time path, right? Fermat principle, but which is dimension time. But a mechanical path, a particle in mechanics, is a least action path, which has a different dimension, 1 by time dimension action. So this has to do with that. So you can connect this with that. So let's not enter into that discussion right now. But one thing know that you will know that a lot of techniques that is invented to describe heat transport, heat diffusion, can be transported into quantum dynamics. Okay, and there is a whole subject called diffusion Monte Carlo, and all these techniques people used, which people applied for heat equation, because of this structural resemblance. Okay, so now let's talk about the free particle, more about the free particle. So you have some differential equation in your math methods course, right? Is it done already, or you will do it later? Not done. Okay, so maybe you will go through all these things again. Okay, now, all these forms of differential equation that appear in physics. Okay, so notice that one more thing, that this is a stationary state solution, obviously, because it satisfies h psi equal to E psi. So therefore, again, you must also be careful about why the word stationary is misleading here. So stationary means something that doesn't change with time, right? But this is not that, right? There is a time sitting there, but it's still a stationary state solution for the So can somebody tell why it is still stationary state? Because ext is ix mod square. So the probability doesn't depend on time. The psi ext basically e to the power minus iet. E is basically h by h bar. So capital H by h bar. So that's why I'm writing it as h. Psi x. When you write the full solution. So if I plug in this psi xt into Schrodinger equation, plug in to this. Or let me write it h psi equal to. If I plug this, you will get this. The stationary solution, because it is the stationary solution. Okay? So that means you have to solve this equation. And once you solve this equation, you can simply get the dynamics by putting e to the power iat by. So that is what we learned about stationary states. That stationary states doesn't change. Only thing change is the phase factor, and that's why the probability doesn't change. So free particle, the free particle wave function is a stationary state solution. That means the probability doesn't change. Okay. Okay, what more to tell about free particles? Actually, there is a little more, but okay, I'll come back to the free particle again, or should I continue to talk about it? No, let's talk about some general solution, then I'll come back to the free particle again. No, let's talk. Let's finish the free particle right. Okay. So now what I'll do is that I will express this full solution, which is the static equation. And this is nothing but something we already discussed. Psi double prime minus k square psi, where k is root 2me by h bar. And you know this solution is for right and left one, e to the power ikx plus b to the power minus ikx. And there is no restriction in energy or momentum, anything. It is just any energy and any momentum allowed solution. And therefore, the psi xt, we know by stationary state, it's simply going to multiply by minus iet. So it is ikx minus, actually it is e by h bar, which is basically omega. Ikx minus omega t. So I is outside, okay, because there is a I here also. And the is the first line. And the second is okay. And we can rewrite this as h cut k in this form. E to the power I k x minus h cut k by m t okay, because omega by k is just h. Okay, I remove that relation. E equal to h cut omega, E is equal to h cut k. Okay, so I can simply write this as h cut by m, and E is h cut k square by 2m and V is H hat K by M. So this is a solution of this form Fx minus Vt plus Fx plus Vt. So just to show you, to bring it this form, that the solution of Schrodinger equation for a free particle is same as that of a plane wave form. Okay. So what more? Okay, now there is a non-trivial statement I'm going to make, because I already told you that this seems to has it's not a normalizable object. So then how to make sense of it in the language of probability? And then what does it mean by a free particle at all? Okay. So let me make a little difficult to digest statement first and then try to justify it. Okay, two more things you can do from here. So you are familiar with the concept of group velocity and phase velocity, right? Okay, good. That will become a useful concept. So the fact that free particle with definite energy and momentum. Actually, let's just leave it. Energy and momentum are same thing. I mean, once you know the energy, you know the momentum. Definite energy is not normalizable in QI. So the consequence of this is there is no physical meaning of this. Okay. But now, how do you describe then a free particle property? So this is one more thing which you should pause and wonder about. That even description of a free particle doing nothing is so complicated. Like it seems to be there is no physical solution. So then what to do about it? So turns out you can describe a particle as a wave packet. So wave packet means it is a superposition of many plane waves. The K should be outside. No, K is inside. So then I can put K square. Dk. So what is this? This means you have a bunch of plane waves which you have added with a weight phi k. Right? This is something you have done, this sort of thing, right? This is the description of a wave packet. So when there are many such wave packets, so what is this e to the power I kx? This thing is a plane wave, right? E to the power I kx, this object minus omega t. But when you add many of them with slightly different k, when you add many of them, this will become this, right? If there are infinitely many of them. So then it physically makes sense to talk about a free particle at a definite position x and t. Okay? So this thing is physical. So now you can show this thing is physical because you can now normalize this. And that is not just this. So you can also choose to choose this phi k in certain way, or you can truncate this sum into some, not go to infinity to plus infinity. So you will get a finite width wave packet. And this finite, so this object that oscillates till infinity is not normalizable. But these finite width wave packets are always normalizable because it truncates somewhere. Okay. So that is a physical object. So that is what we know as physical free particle. Right? That is what we know as physical free particle. So the physical free particle is actually described by this. But this e to the power I kx, which is a legal solution of a free particle wave function, doesn't represent anything physical. Okay? So that is what the point to notice. Now you can also check, so this is an important thing to notice, that this should be also a legal solution. Right? This should be also a legal solution of Schrodinger equation. So that you can check by plugging this into xt equal to E psi xt, and that is also becomes a legal solution, or let me write it in this way. So this is a solution of del 2 psi del x2 h bar del psi. So check that. It's a very simple solution. Just check that. So the let's take a step back and again revise that what just happened. So a legal solution of this equation is this e to the power ikx minus omega t, but that's a non-normalizable wave function. That's a non-normalizable solution. So it doesn't represent a free particle in physical sense. Although we use the word, again there is a language problem, but we use the word that as a free particle solution, but it's not a physical solution. But what is physical? A superposition of them, because now it has a definite position, and now it corresponds to what you know as a free particle in classical mechanics, and that is also a legal solution of that. But then why this thing is still useful? This is useful because this helps you to construct that solution by superposition of that. So I am telling everything about this in a way without touching the knowledge of Fourier transform and all. But you know, in Fourier transformation, if you have done that, what does it mean? It means you can add, you can express any well-behaved function in a harmonic basis. Right? That is basically the statement. Okay, everybody is clear about this point. This is a conceptually puzzling point, although technically it is very easy. Technically, all you have to do is calculate this. So if someone, for example, asks you to do this problem, let's say you will see this kind of problem, that I am throwing a free particle into some potential. Yeah? So how you actually deal with this problem, if you want to deal with it, make it a practical problem, is you work with this wave function, this superposition wave packet. And then you solve the problem, that what is it probably to reflect, transmit, so which is what we'll do in next 1-2 classes. And this is, you will see that this is actually a very important problem, because most people in semiconductor applications basically solve this problem. But this conceptual point is very important. Okay, so what more should I say? Okay, one more thing. Then how do you refer this group velocity phase velocity point? So as I already argued that psi kxt. So a psi kxt, or you can also write it as psi ext. So this thing is not a physical. So a free particle wave function that has a definite momentum. That has a definite momentum or definite energy is not a physical object. So not a physical object. But then if you want to understand that what does it mean by then velocity of such a free particle, that's why this group velocity and phase velocity come. So you know there is this concept of phase velocity and the group velocity of a wave packet. And the interesting point here is that if you calculate the group velocity, which you know is d omega dk, that comes as h cut a k by m, and the phase velocity is just omega by k. So this comes as h cut k by 2m, because omega is h cut k square by 2. So the phase velocity is half of group velocity. You probably have also learned it in previous semester, right? In the world of quantum mechanics course. So I'm just explaining all those things from a more technical standpoint. So when you describe this wave packet, you generally take this group velocity. It's a matter of convention which one you take, because one is just the half of other. Okay, what else? Okay, that is basically everything I wanted to say about wave packets and free particle. So now I will move on and talk about the next level of problem, when the potential is not zero, which means it's not a free particle. Okay. So before I go to that, any questions up to this? Yeah. Yes. Yes. Sorry, say that again. Yes, that's a superposition. Yes, superposition of the plane wave solutions. Hmm. No, you get a k plus delta k, right? That's the uncertainty. Yeah, if you know the x precisely, you don't get any k value, right? That is what you know. Yeah. So, but no k value, right? That is the energy. This is the thing about position and momentum, right? Any such two conjugate variable. That if you measure and find a particle in a definite place, that means it is a superposition of all the possible k. Okay? And opposite also is true, which means if you know it at a definite momentum, then it's a superposition of all the possible x. So this is basically restating that same statement. Right? Makes sense? Okay. Everyone else? Okay, good. So now I will talk about. So this is what is interesting, that we spend so much time to describe nothing, that is a free particle doing nothing. Okay? Now you do, and actually you will see that what we'll do now is much easier than this. It boils down to solving a differential equation, whatever we'll do. This is actually another interesting thing to notice, a philosophical aspect, that more advanced you will get, a description of one particle will get more complicated. But it will make other things easy. Like for example, when you go to QFT, you will see you cannot even make sense of an isolated, not even QFT, in quantum mechanics 2, you will learn Dirac particles, right? You will realize to describe one particle, you have to bring infinitely many particles. So that will become even more strange. And later you will even see that there is no particle. Everything is field. And then there is another way of saying there is no particle, no field. It's whatever you describe it as. So basically the point is the world is a concept. Okay. What is true and what is not true is very difficult to say. And it's only that what we learn first we think as true. But what we learn next, then we see, okay, it doesn't match with what we learned first. But then if you think carefully, what you learned first, that also doesn't make sense when compared to what you learn next. Okay? Anyways, I should not muddle with your head more, but you will realize those things more you learn physics. And it gets more and more interesting. Even simple things gets very interesting. Okay, so we said that. Okay, before I do this, in the remaining time, let me tell you something else, that why I am doing this. Okay, so now we said that. So remember that earlier we argued that IH bar d psi dt is H psi and H psi is equal to E psi. Right? These are the two main problems you need to solve in order to know the dynamics. Right? And the problem boils down to this solution is very important. So let me give an index, because I told you earlier that let's say you want to know take a arbitrary state phi 0, and you want to know where this phi t goes. That's what we discussed last time. So this becomes basically e to the power minus iht by h bar, and this is e to the power minus iht ient by h bar psi n n phi. So as I'm repeating the same statement, that once you know this solution, then this is very easy to find any evolution, because it becomes a problem of multiplying some vectors and taking some dot products and multiplying it with a phase factor and simply summing over them. So how does this problem look like in general for a continuum system? We discussed thoroughly how it looks like in a discrete system. So there what you have to do, so let's say you are solving this equation H. So now I'm talking about a general problem. So let's not talk no more about free particle, but it's also applicable for free particle that we have seen. Del 2 del x2 plus Vx psi x So you have to, this is the equivalent of this. And once you solve this, then you have to solve the dynamical equation, which is I h bar psi n xt dt, d psi n and xt, this h psi. I'm not writing the full form of h, but this is same h. Okay. So basically that means you have to solve this problem. If you know this solution, you can solve this by the same token. And that is what we'll do for, I think, next 1-2 weeks. And various problems we'll learn how to solve this. And it's a very trivial, not trivial, but conceptually simple, that it's a differential equation, how hard it can be. So, and actually it turns out there are issues arises and one needs to do various technique, but conceptually at least it's a differential equation. So let's say I rewrite this is in form. So h I n x n x, and let's assume that the spectrum is numerable, which is not always true, which means En is the possible energies when you measure. There is no guarantee a priori that this is a discrete spectrum, right? We know that, of course, from experience and otherwise, but a priori there is no reason to assume that. So it could be continuous also. So for now, I am assuming it's a discrete spectrum, at least numerable. So numerable, and that there is some order like that. So this is the thought sequence, and it must satisfy, the solution must satisfy this. So this solution must be n must satisfy delta m. So by n is basically, I imply this h n e n. Actually, since I'm using psi n, that means so psi n satisfy this, and that means in continuum, that means psi n x psi n is delta nm. They are orthonormal, and that means psi n star x psi n x. So the legal solutions must be like this. So now I am trying to find all the possible conditions as I can without actually solving the problem, because then when I search the solution, I must satisfy all these properties, that it is a solution of this equation, it must satisfy this, and then we'll see another set of conditions is boundary condition. It's a second order differential equation, you need 2 boundary conditions to solve it. So now once you know the solution, then you know this is true. Any arbitrary wave function, let's take some phi x at t equal to 0, you should be able to expand it bn psi x, some arbitrary wave function, and then if I know this, then I want to calculate this wave function at time t. It is nothing but that's all we have to do. We have to, once we solve this equation, then we have to just sum this object, okay, to get some time dependence form. And what more? So what is the unknown here? What is the unknown quantity in this problem? Bn, right? So we have to figure out what is the Bn. So let's say I have solved the problem and this is a known quantity. How do you know the Bn? Somebody knows? Using orthonormality, right? So you have to do Bm is minus infinity plus infinity psi So because of this property, if I multiply both by psi m, this property will give me delta function, this will give me phi and psi product. Okay. So your only job is to basically multiply this and integrate this. All these things are very trivially done in Mathematica. In when I took the first quantum mechanics course, the whole course was differential equation solving. Now you don't need to spend it, you can do it in Mathematica very quickly. Like we have to learn all these orthogonal properties and everything. Yeah. So what else? Yeah, that is everything basically. So one more thing I want you to show. Yeah, is this okay? No, I think that's all. So now what I'll do is I will do two more things to show the generic expression of expectation value. And so how do you calculate this expectation value in this form? And then from next class onwards, we will take specific examples. I will do a generic example first, then I'll go for particular example where the psi. For example, if you have done particle in a box, right? So particle in a box is what? This problem where the Vx is 0 when x is L by 2 to minus L by 2. And it is infinity otherwise. So this. So here the phi n is, the psi n is root 2 by L sin n pi x. Actually, no, I made a mistake. What mistake did I make? Huh? 0 to L. Because if you do this, you have to put cos here. Okay. So this is 0 to L. Okay. So now you know this solution with n, en as n. I think something like this. Then you know everything, right? Then if I give you a particular waveform, let's say I give you a phi x 0, which is of some form, some fx, some arbitrary fx. Right? Then all you have to do is do this set of equation. So some arbitrary fx, how it time it deforms, that kind of calculation you can do very easily. Okay, so I'm just saying the general structure of this calculation. Later it will become just plug and play. So now I'll finish with expectation value. That the most important thing in quantum mechanics is, of course, the expectation value that connects with experiments. So how do you calculate this? That's also very simple. So let's say I have some arbitrary operator and I want to calculate the expectation value in state psi. So this is the symbol of that. So that will become okay. And so let's take the example of H psi. Let's say I want to calculate the energy expectation value. So what should I do? This is dx psi star xt h psi xt. Okay, and that is h acting on psi xt. That becomes. So let me make it simple by going to the energy eigenbasis. Let's not call it psi, let's call it phi, because I'm using the psi for eigenvalues. So phi is some arbitrary state, which is not an eigenstate. It can be eigenstate, but need not be an eigenstate. So then it becomes dx dn. So I'm using this term. We have done this in discrete basis. I'm just rewriting it in continuum basis. Phi. Now I can use psi n star x times bm e to the power minus I em t h psi m. Okay. I'm just expressing the phi in terms of this bm. Okay. So that's what we have to calculate, and this is a very simple calculation. I mean, conceptually, e to the power I en minus em t by h bar bn star bm dx psi n star x h phi n x. Okay, so you have to do one integral and some many things, and this is also a very trivial calculation because Okay, because this will give you, this is a eigenvalue, right? This is a eigen solution. So this should give you a I n minus bm t by h bar bn star bm em. So dx psi n star x, right? So that's all you have to calculate. Now this is also very simple because this is a delta function, right? Because of orthogonality, because of this, right? So this is nothing but En Bn mod square. So any A for H, it's particularly trivial because you have calculated the Bn already there. All you have to do is plug and play. Just plug this in and do. These are very trivial. These are, you write these 3-line codes in Mathematica to do these calculations for any problem. Okay, not any problem, for all textbook problems that you encounter in quantum mechanics 1. Okay? So now if I give you a, so now try this. That's what I give. So if I give you a that commutes with H, the calculation will be similar because the action of that A on this I will again be like this because they have same shared eigenvector. But if I give you A that doesn't commute with H, then this equation will be complicated. So try to work out that. Okay? We did that already in discrete basis. Just do this in continuum. Okay, that is where I end. And in the next class, what I will show you is basically how to solve this problem for various scenarios, various potential. Particle in a box you did, but we'll do various other things. Harmonic oscillator, and so we'll first lay out a general strategy. We'll see that as far as you can do without solving the problem, then we'll actually solve the problem. So this is a very important skill which I cannot overemphasize enough, that you must learn to know the structure of the problem in as many different ways possible without solving the problem. Because in textbook problem, generally what happens, you know the problem has a solution, and in exam or course, you know, even if you don't know the solution, someone else does, your instructor does. But in research, you don't know that, right? Not only someone else does, nobody knows the answer, right? So these kind of consistencies and these kind of things are very important to be on top of your head. Okay. So spend some time thinking about it. It's very easy. I hope you are realizing, those who have paid attention till now, that the course is getting easier. And that's what I promised you earlier, that if you have paid attention in first half of the course will only get easier, and quantum mechanics 2 will be actually easier than quantum mechanics 1. But if you have not paid, then I don't know. then I don't know how it is going. But still, it is a differential equation solving, how hard it can. Okay, I will go for lunch now, but I think I will be back around 1:30 or so. You guys can start coming after that for your exercises.